Hi everyone, in this tutorial we're going to work through a couple of examples in which we solve separable differential equations. Given a differential equation, we say that it's separable if we can write dy dx as being equal to the product of a function of x, so say f of x, and a function of y, so I'll say g of y. And as soon as we're faced with this type of scenario, the whole idea behind separating the variable is to gather all of the y's on one side of the equation and all of the x's on the other. And looking at this generic equation, we quickly see that we could rearrange this to write dy over g of y equals to f of x times d of x. Once that's done, we find the solution to the differential equation by integrating the left-hand side with respect to y and the right-hand side with respect to x. And that's the whole idea behind separating the variables. That being said, let's work through this example. We need to find the general solution to dy dx, which equals to 8xy squared. So if I go ahead and write sol as in solution, looking at dy dx, which equals to 8xy squared, and comparing this to the generic differential equation we have here, we quickly see that we can think of the right-hand side as being a function of x, this 8x here, multiplying a function of y. So we can separate the variables. If I do it in steps, I could start by multiplying both sides by dx. So that would be dy equals to 8xy squared times dx. And then if I divide both sides by y squared, that would lead to dy over y squared equals to 8x dx. Now we see quite clearly that we've separated the variables. All of the y's are on the left-hand side and all of the x's are on the right-hand side. So we integrate the left-hand side with respect to y, and we integrate the right-hand side with respect to x. In other words, we can go ahead and write that the integral of 1 over y squared dy equals to the integral of 8x dx. Now by all means check, but integrating 1 over y squared with respect to y leads to negative 1 over y, and that's equal to the integral of 8x. And that's 4x squared plus some constant of integration, c. Now I rearrange this to make y the subject, and for that I multiply both sides by y, so that would be negative 1 equals to y times, in parentheses, 4x squared plus c. And finally, dividing both sides by 4x squared plus c and rearranging leads to the general solution, y equals to negative 1 over 4x squared plus c. And that's the general solution for this differential equation. We move on to question B, in which we need to find a particular solution given y equals to 1 when x equals to 0. Well, for that, all I have to do is copy the general solution that I have here, replacing y by 1 and x by 0, and I'll then solve for c. So that would be 1 equals to negative 1 over 4 times 0 squared plus c, and that becomes 1 equals to negative 1 over c. And we quickly find c equals to negative 1. And in an exam, I would go ahead and box that result to make it clear to the examiner. And finally, I write my final answer, replacing the c that I have inside the general solution by the c that we just found. And that would be y equals to negative 1 over 4x squared minus 1. And we could leave this as a final answer. It would definitely be accepted. But to avoid having something negative like this on the numerator, we could take a factor of negative 1 away from the numerator and the denominator to state our final answer as y equals to 1 over 1 minus 4x squared. And we're done. We've just found the particular solution for this differential equation given y equals to 1 when x equals to 0. Let's look at one more example. In this case, we're asked to find the general solution for the differential equation that we have here. That's 1 plus x times dy dx, which equals to 1 plus y squared. And we'll then have to find a particular solution given y equals to 1 when x equals to 0. So let's go right ahead. I'll write sol again, as in solution. And so the first thing we need to do is find a general solution. Now, looking at this differential equation, it's not immediately obvious that this is a separable differential equation. But the first thing I would do is rearrange this equation to make dy dx the subject. For that, I divide both sides by 1 plus x. And that leads to dy dx equals to 1 plus y squared over 1 plus x. And looking at the differential equation now, we can think of this as a function of y, which is being divided by a function of x. And so we'll definitely be able to rearrange this and separate the y's from the x's. Indeed, multiplying both sides by dx and dividing both sides by 1 plus y squared leads to dy over 1 plus y squared equals to dx over 1 plus x. Now we see we've separated the variables. We have all of the y's on one side and all of the x's on the other. And so we integrate the left-hand side with respect to y and the right-hand side with respect to x. In other words, we can now state that the integral of 1 over 1 plus y squared dy equals to the integral of 1 over 1 plus x dx. Integrating 1 over 1 plus y squared with respect to y leads to inverse tan or arctan of y. And that's equal to the integral of 1 over 1 plus x. And that equals to ln of the absolute value of 1 plus x. And of course we have our constant of integration. Finally, to write the general solution, we use the fact that inverse tan and tan are inverses of each other to state that y is equal to tan of ln of the absolute value of 1 plus x plus some constant of integration, c. And that's the general solution for this differential equation. Now that we have that, we move on to question B. And here we have to find a particular solution to this differential equation given y is equal to 1 when x equals to 0. Well, just as for the previous example, all we have to do there is copy the general solution that we just found, but we'll replace y by 1 and x by 0, and we'll then solve for c. So that would be 1 equals to tan of ln of the absolute value of 1 plus 0, so that's just ln of 1, plus c. But since ln of 1 is equal to 0, this becomes 1 equals to tan of c. And just by looking at this, you can probably tell right away what c is, but for the sake of being rigorous, I'll go ahead and apply the inverse tan to both sides of this equation. In other words, I'll go ahead and state that inverse tan of 1 is equal to c. And since the inverse tan or arctan of 1 is equal to pi over 4, we can state that c equals to pi over 4, which I'll just box, and I'll state the final answer. Remember, all I have to do there is copy the general solution we found previously, and I'll replace c by pi over 4. So that would be y equals to tan of ln of the absolute value of 1 plus x plus pi over 4. And that's the final answer. And now that we've worked through these two examples of separable differential equations, we'll hopefully have a better idea of what separable differential equations are and how to solve them. And that's it for this tutorial.